Hello everyone, resuming from last time, I'm going to introduce you about NFA to DFA conversion in today's video. The right table shows the D trend, which is the transition table, and we first need to calculate the start state A by computing the epsilon closure of 0. The epsilon closure of S is defined as the set of NFA states reachable from NFA state S on epsilon transitions alone. For example, state 1 is reachable from state O on epsilon transition, so we can add state 1 to the result set of epsilon closure of 0. And the 0 is the S in this case. And because we also add a 0 move, we also add 0. And as I mentioned earlier, we also add state 1. And state 2 is reachable from state O on epsilon transitions alone through O to 1 to 2. So state 2 is in the result set of epsilon closure of 0. And state 3 is not included because we have to pass through a transition to reach state 3 from state O. That is, the state 3 is not reachable from state O on epsilon transitions alone. And state 4 is reachable on epsilon transitions alone through state O to 1 to 4. So state 4 is included in the NFA state of the corresponding DFA state A. And state 5 6 are not included for the same reason. And state 7 is reachable from state O through state O to 7 on epsilon transition alone. And states 8, 9, 10 are not included in the NFA state of the corresponding DFA state A because they are not reachable from state O on epsilon transitions alone. So once the start state of DFA state is computed, which is state A, the other states are computed by epsilon closure of move of d comma A. So move of d comma A is the set of NFA states to which there is a transition on input symbol A from some NFA state S in T. So let's first compute epsilon. Before we compute epsilon closure of move of A comma A, let's first compute move of A comma A, which is 3 comma A, and move of A comma A. So remember the definition of move of D comma A. The NFA state of A is O1247, and we need to find out the states that are to which there is a move on input symbol A. So from state O, there's no move on input symbol A, and we can find input symbol A here, and there is a transition from state 2 to 3. So let's check whether state 2 is in the NFA state of A, because state 2 is included in the NFA state of A. So state 3, which is the state reachable on input symbol A from state 2, we add it to the move of A comma A. So state 3 is included here. And in case of state 8, there's a input symbol A to state A, and If we check state 7, where there's a input symbol A transition to state 8, and state 7 is in the NFA state of state DFA state A, so we include state 8 to move away, A, which is the set of 3, 8. And as move of A, returns 3, 8, we can compute epsilon closure of 3, 8, and epsilon closure of 3, 8 is going to give us 1, 2, 1, 2, 3, 4, 6, 7, 8, because epsilon closure of T, we compute all the epsilon closure of 3 and epsilon closure of 8. So let's first compute the epsilon closure of 3. It is the set of the NFA state to which are reachable from state 3 on epsilon transitions alone. So if you see state O, it is not reachable from state 3 on epsilon transitions alone. And in case of state 1, we can reach state 1 through state 3 to 6 to 1 on epsilon transitions alone. So state 1 is in the result set of epsilon closure of 3, 8. See, it's included here. And state 2, we can reach state 2 from state 3 to 6 to 1 to 2, on which the input symbols are O epsilon. So 2 is in the result. And 3, no, you cannot reach 3 on epsilon transitions alone. And no, actually, let me repeat that. You can reach 3 from state 3 on 0 move. So we add state 3 as well. And in case of state 4, you can reach state 4 on epsilon transitions alone through state 3 to 6 to 1 to 4. And 5, no, we have to pass through state input symbol B to reach 5 from state 3. And state 6, we can reach state 6 through state 3 to 6 on epsilon transition alone. So state 6 is in the set, and state 7, we can reach from state 3 through 3 to 6 to 7 on epsilon transitions alone. So, and the rest of 8, 9, 10 states are not reachable from state 3 on epsilon transitions alone. For example, to reach 8, you have to pass through symbol A. And these are all the elements for state 3 at first epsilon closure of 3. And next, let's compute the epsilon closure of 8. And there is only one state A on which there's epsilon transition, to which there is an epsilon transition. So we add only state 8 because we can reach state 8 on 0 move. So the result NFA state of epsilon closure of 3, 8 is 1, 2, 3, 4, 6, 7, 8. And in this case, we add new DFA state B because this newly calculated NFA state is not in the existing NFA states. So we add the DFA state A, which is new DFA state B. So dtran a comma a is b because we compute dtran a comma a by epsilon closure of move over a comma a. So we repeat this process to compute dtran a comma b. So to compute b dtran b a comma b, we compute epsilon closure of move over a comma b to fill in dtran a comma b. So same as earlier, the NFA, the states in NFA state 01247, which is the corresponding DFA state of A, we find out the state on to which there is an input symbol B from some states in this NFA state. So here is an B transition to state 5 from state 4, and see that state 4 is in the NFA state of A. So because the state 5 is the state to which there is an symbol B transition from state 4. So we add 5 to the move of A comma B, and for other states to which their speed transition 9, 10, the states 8 and 9 are not in the NFA state of A, so only 5 is in the result set of move of A comma B. So we compute epsilon closure of 5, which is the epsilon closure of move over A comma B, and if we compute epsilon closure of 5, so we try to find out the states reachable from state 5 O, and O not reachable from state 5, 1 reachable through 5 to 6 to 1 on epsilon transitions alone. So state 1 is in the epsilon closure of 5, and 2 you can reach from state 5 to 6 to 1 to 2, which on which the transitions are all epsilon, and 3 no, you cannot reach 3 on epsilon transition alone, and 4 you can reach 4 from 5 through 5 to 6 to 1 to 4 on epsilon transitions alone. And in case of 5, because 5 you can reach from state 5 to 5 on 0 move, so we add state 5 as well, and state 6 it is included in the result set of epsilon closure of 5 because you can reach it from state 5 to 6 on epsilon transition alone, and state 7 you can reach from state 5 to state 7 on epsilon transitions alone through 5 to 6 to 7. So 8, no, you cannot reach state 8 from state 5 on epsilon transition alone, and state 9 and 10 are not reachable as well from state 5 on epsilon transitions alone. We have to go through state B transition to reach them. So 1, 2, 4, 5, 6, 7 are the result NFA states of epsilon closure of 5, and this NFA state is not in the existing NFA states found so far, so we add it to our new DFA state, which is named as C. So D trend A, B is going to be C, which is the epsilon closure of move over A, B. So we fill in the table A, B with DFA state C, and we repeat this process for the rest of the DFA states. So to compute the D trend B, A, we compute epsilon closure of move over B, A. So as same as earlier. So first we check the NFA states of DFA state B, which are 1, 2, 3, 4, 6, 7, 8, and let's find out the states to which there's an input symbol A from some state in NFA state of B. So if we look at the input symbols A, states 3 and 8 are the states to which there's an input symbol A from some state. So if we look at the some state, they are state 2 and 7, and because they are included in the NFA state, some NFA state of B, C, the states 2 and 7, which have A transition to state 3 and 8, are in the NFA state of B. So we add state 3 and A because they are the states to which there's an input symbol A from some state in NFA state of B. So move of B, A is 3, 8. So we compute epsilon closure of 3, 8 to compute the trend B, A. So epsilon closure of 3, 8, we have already computed it earlier here. So the NFA state is 1, 2, 3, 4, 6, 7, 8, and we see that the DFA state already exists in the D trend. So we fill in the DFA D trend B, A with B, and let's go to compute D trend B, B, and B, B, the NFA states are 1, 2, 3, 4, 6, 7, 8, and move let's first compute move of B, B. So if we compute move of B, B, state 5 and 9, 10 are the states to which there's a B transition from some state, and state 5 and 9 are the states that have B transition from some state in the NFA state of B. So we add state 5 and 9 to the result set of move of B, B. So next we compute epsilon closure of 5, 9, and as we have already computed epsilon closure of 5, we add all these 1, 2, 4, 5, 6, 7 to the result set of epsilon closure of 5, 9, and we compute the epsilon closure of 9, and state 9 is the only transition that has epsilon transition that can be reachable on epsilon transitions alone by zero move. So the result set of epsilon closure of 5, 9 is going to be 1, 2, 4, 5, 6, 7, and 9. And this new state is not in the D trend, so we add and name it as DFA state D. So D trend B, B is D. And we repeat these processes same as earlier, and if we repeat that, the D trend is going to be filled as on the right table. And using this D trend, we can convert the NFA on the upper right to the corresponding DFA, deterministic finite automata. So using this table, we can construct the DFA accepting A or B clinical closure ABB, which is the same regular expression representing the NFA up here. So DFA state A, we connect state B on with input symbol A. So A to B, we have label from state A to B, and we connect with B transition from state A to C. A to C with it is connected with B transition, and you connect B to B with A transition, B to B. You have A transition from B to B, and from B to D, you connect with B transition. So from state B to D, you can connect with B transition. So this final DFA can be constructed by repeating this process, and see that the state E is the final state, and the final state is the state that has the final state of the corresponding NFA state, in which the NFA state up here, state 10 is the final state, and because DFA state E includes state 10, which is the final state of the NFA state, the DFA state E is the final state of the converted DFA from the NFA up here. So if you try some of the string, maybe from A to C to B to D to E, B, A, B, B, and this DFA is going to accept all the language that can be created from regular expression A or B, clinical closure ABB, as the NFA state, NFA accepting A or B, clinical closure ABB. So B, A, B, B, we can try here on the non-deterministic finite automata O to 1 to 4 B and A, B, B. So O1 to 4 to 5 to 6 to 7 to 8 to 9 to 10 is the root of BABB, which is also possible from the corresponding DFA through A to C to B to D, D to E, which gives us the string BAAB. Actually, BAAB you can reach by B and through B and A. Was that BAAB? Yeah, BABB. So BABB. Yes. So you can reach through O 1 to 4 to 5 to 6 to 7 to 8 to 9 to 10, which gives us the string BABB, in which the epsilon transitions are concatenated, and you can derive the same string in the corresponding deterministic finite automata of the non-deterministic finite automata through A to C to be B A B A B B, A to C to B to D to E. So you can try deriving other strings from NFA and the same string to in DFA. So in today's video, I have discussed about NFA to DFA conversion, and in the next video, I'm going to talk about the syntax analysis, and I'll finish off here and see you in the next video. Goodbye.